In this series of videos I'm designing a Z80 based computer system. I'm trying to use discrete logic as much as possible in the design, so I'm trying to avoid the use of large-scale integration devices that are very popular these days, and they do greatly simplify the design of a system like this. But I'm specifically trying to avoid them because I think it will be far more interesting for some people to see a discrete design just using discrete TTL chips rather than the large-scale devices. It will also allow me to show the inner workings of how those large-scale devices actually operate, because the circuits we're developing here are really nothing more than the way that the large-scale devices operate, albeit in a greatly simplified manner. And I'm also trying to show that the development of a machine like this can be broken down into discrete modules, and that allows you to develop and design each part of the system independently. All has to work together, of course, but you don't need to look at the entire system as one huge task. It can be broken down into individual parts. That in turn can make it far easier if you work on these machines, if you repair them or want to modify or even further the design of some existing machines. Then rather than opening the schematic and seeing it as one huge circuit, what I tend to see when I look at a schematic for an old machine is lots of individual discrete blocks of circuit where each part has a specific task. Quite often the way they're drawn can make it difficult to see that, because you might find on a single schematic it contains more than one function, and that's just a limitation of having to draw circuits on schematics that you don't want extending over hundreds of pages. So as I said, what I'm trying to do here is develop a computer based around the Z80 using vintage methods. I'm not necessarily trying to design a vintage computer. This is just the approach I'm taking and using discrete circuits. So I'm not showing all the schematics through these videos. I'll show some of them. I'll show the schematic for this module in this video because it will help with the explanation. In the previous video we designed the receiver module for our RS232 communications module, and in this video we're going to look at the transmitter for the RS232 module, and that's what I've got on the breadboard here. So it's actually those four chips. The fifth one is just so that I can tidy up the incoming clock. The clock I'm using for the two modules, the receiver and the transmitter module, is derived from the Z80 main clock. If you recall, there's a divider on that main clock, and one of the outputs is 625 kilohertz, and that's what I'm using to drive our two RS232 modules. So that comes in, goes into a divider, and so what we have here is everything that's needed to create an RS232 transmitter. If we look at the packet again for what we're trying to put together and send out, it's fairly straightforward. We're going to use 8 data bits, and again, the way I've designed these circuits, they are modular within the modules, so you can change any aspect of this to suit your particular requirements. So if you want to change the baud rate, you can do that. But this is the packet type I've selected. I'm going to use a single start bit, 8 data bits, and 1 stop bit. So this is what we have to try and feed out. So normally when I start a design like this, I'll create a simple block diagram, and these are just the sketches that I make as I start the design. I turn them into a more formal form later on, but I've been asked to show some of this, so this is what I do. So we've got the incoming clock. This is the master clock coming from the Z80. We've got the divider, so that's this device. It's an 8-bit binary divider or binary counter, and by selecting the appropriate output from that we can select different baud rates. That's used to drive a shift register, so that's this device at the top right. It's an 8-bit shift register. It's a parallel in, serial out of course, and that will be connected to the data bus of the Z80, so the Z80 will be able to load it with the required data byte, so we'll be sending 8-bit data. We also need the stop bit and the start bit, so we're actually sending 10 bits of data. We've only got the 8-bit shift register. So for the other 2 bits, we've got a bit we feed in for the stop bit, and then we've got an extension for the start bit. So we've got 9-bit shift register in effect with a load of the 10th bit. So to extend the shift register is very straightforward. You can actually daisy chain 2 shift registers together, and you might want to do that if you want a more flexible system and you want to extend the number of bits to an arbitrary level. But if you want to add just a single bit as we're doing here, we can just add a flip-flop. That's all shift registers really are internally. They're a series of daisy chained flip-flops, so we can extend this by adding 1 or more additional stages, which is what I've done. And then when we load the shift register, we also initialize the flip-flop to the correct value or correct level for the start bit, and then when we start shifting, we shift all the data out of the shift register through this latch, and then we end up feeding through the data byte, and of course we start with a start bit, and the stop bit is shifted into the bottom of the shift register when we start shifting. So we have everything we need to shift out the entire 10-bit packet. But we need some form of control for this to start it and also to stop the shifting at the end of the packet. We don't want it to carry on shifting out bits because that would cause us some issues, and also we need the Z80 to be able to load this and zero everything at the same time. For example, the divider must be zeroed when we load the shift register, otherwise the first clock edge for the shift would be in a variable position, an unknown position, and the length of the first bit would be indeterminate. So we have some control logic. It's very simple, and that's just used to control the various parts of the circuit. And so we have a data output, and then we have a start input, and I've designed this in a similar way to the PS2 module that we looked at a while ago. So the data comes out, goes to the serial port, and for the Z80 it needs some way of determining when the send has finished, because that's obviously quite slow compared to the speed of the Z80. So this system outputs a busy signal, and we'll look at that in a minute, but that busy signal can be used to trigger an interrupt. So the Z80 will generate an interrupt, load the next data byte, start shifting, and then when that's finished it will trigger an interrupt, and it will keep going round, and it makes very efficient use of the Z80. Indeed, it can send at a very high baud rate and only use about 1% of the resources of the Z80. So again, that's part of the design philosophy, is when you're designing with discrete circuits, it's very like when you write code using assembly language. You have much more control over the inner workings down to a low level. You can actually make systems more efficient using discrete logic than you can with higher level large scale devices. And that's what I'm aiming for, is try and get a low IC count but an efficient circuit, and also one that can be expanded and extended and modified if that's what you want to do. So before we look at the circuit, I'll power this up. So I'll switch the power on. You'll see on the scope we have various signals. So this is now powered up. I'll turn the main clock on. In fact, before I do that, I'll turn on the second signal source that we've got coming in. And you'll see on the scope, this is just a series of low-level pulses. And these are the start or the load pulse that would normally come from the Z80. This would normally be connected to an in-out port, and so the Z80 would just do a write to a port, and it would send the data byte it wants to be transmitted. These pulses are normally only a microsecond in duration, but I've extended them here to about 50 microseconds just so we can see them more clearly on the scope, because otherwise on this scale, because the RS-232 is relatively slow, we probably wouldn't be able to see them if I reduce them to 1 microsecond. So what I'll do now is turn on the master clock as well. And so what you can see here is the yellow trace is the clock going to the shift register, and again I'll show you the circuit in a minute. And this rate is controlled by the divider. We then have the control circuit that is triggered by the low going start pulse. The purple is the busy signal going out. That's what would be used to generate the interrupt and inform the Z80 that the circuit's finished sending, or you could just pull it, of course, if you didn't want to use an interrupt. And the green trace is the data going out of the shift register, or rather the latch that's following on from the shift register. And this white jumper can be used to select different baud rates. So as with the receiver module, to select a different baud rate, all we do is we select different outputs of the divider. So if we go up in speed, you'll see that the data rate is getting faster and faster, and we can go the other way and it will slow down. So you can set up whatever division ratio you want by changing the divider. The rest of the circuit can stay the same, but you can just set up whatever division ratios you require. As I said, this IC here is just to square up the incoming pulse, actually for the blue pulse. So that would not normally be part of the circuit, it's just these 4 ICs. And the IC in the center left and the bottom left are the control logic for this system. So looking at the circuit, so what we have is the divider. So the clock comes in, generates the various clock signals, and we select whichever one we want, and they are used to clock the shift register. So data's loaded into the shift register by the Z80, and as part of that action, and it's by taking this line low that the Z80 will load that shift register. But you can see this is connected to quite a few other things. So it will also set the first latch into the correct required state, and that will give us the start bit. So that's the first bit on the left we can see here. That will make sure that the start bit is correct for the RS-232 protocol, and then the data will start shifting through and coming out. And notice we have a data and a not data, so it's very flexible, and which one you use will depend on the type of driver you're using. We need the stop bit as well. The stop bit's always going to be low, so what we can do is just connect the serial in of the shift register to ground, and that will effectively be our 10th bit of the stop bit. Or if you just carry on clocking, then you can have more than one stop bit. If you want to increase the number of bits you're sending, then that's where this comes in. So we have a counter here. The counter is actually loaded, it's not zeroed, but it's loaded when the shift register is loaded, and it's loaded with a value dependent on what we set on the load inputs, of course. We don't actually use the outputs from this, we use the overflow output, and that's used to terminate the send sequence, and that is used to inhibit both the divider and the shift register. And because this counter is clocked by the output of this divider, when we disable this, it also stops this from counting as well. This is an up-down counter, so you've got 2 options for using this. You can either load it with a value that's its overflow value minus the count that you want. In this case that's 6, because I want to count 9 clock pulses, or you can, and then we count up, or you can count down and load it with the value that you want. So for example, you could load 9 and count down and then use the underflow So it's up to you how you go about using this, but the point is you could load this from a latch, and so by selecting different numbers of bits you can easily cater for that by the value you load into this counter. This flip-flop at the bottom here is just enabled at the start, and then it's disabled at the end, and it's used to control the output. It also has a busy and not busy output, so again we have an option here as to which line we use to either generate an interrupt or to be polled by the Z80. And by arranging it like this, what you can do, for example, is you could connect either another shift register or another couple of latches, flip-flops, to the serial input, and you could load those from something, for example, like a parity generator that was monitoring the data coming in. And that way, if you want to, you can very easily extend this design to include a parity bit. You can, as I've already said, add one or more stop bits, and all you'd have to do to make sure all the bits are clocked out properly is load an appropriate value into this counter. The rest of the circuit will operate in exactly the same way. You could also, as with the receiver module, put a selector, data selector, on the output of the divider and use a latch to select the baud rate, so you could automate that in a similar way to a UART. So this is very similar to how a UART works internally, except that it has the latches, etc., and the selectors to select parity, number of bits, that sort of thing. But the circuit works in it's not the same as this, but it works in a very similar way to this. But what I'm trying to get across here is that when you start with a circuit like this, you can very easily expand it. And because this module is a separate module to our main design, you can build this, make a new version of it, plug that in, change it, make another version, add to it, expand it, add parity, whatever you want, and you don't need to redesign your Z80 processor or computer. So you can break the design down into discrete steps and discrete blocks. This even works separately to the RS232 receiver module. You can design them completely independently. That's also why I used a separate divider for this circuit. It also allows us to have different baud rates for the two, although in reality you could still use a single divider, have it running all the time, and then gate the various inputs depending on what baud rate you wanted for each of the two modules. So there's hundreds of different options that you could go for, and what I'm trying to show here is a basic way that you can go about designing the circuits rather than trying to show you a specific circuit. I'll be using something similar to this in my final design, but that doesn't mean you have to. This is just a starting point. The book goes into far more detail about this sort of thing and the various options, but hopefully you can see that by designing your own discrete version you get a very a lot of control over exactly how the circuit works, and you're not encumbered with the complexity of the large-scale devices when probably 95% of what's in them you don't actually need for your particular design. Just a final point here, you may have noticed this inverter on the output of the divider, and the reason that's there is to make sure we don't end up with half a clock period on the start bit. This makes sure that when we reset everything, the first clock edge that will essentially clock the shift register is exactly one full bit duration after the start. You remove this, you'll get half a bit, and that's actually how you can go about generating half bits if you want to. You can just invert the clock and then use the resulting clock that comes out of that inverter to generate your half bit duration. So hopefully this all makes sense and you can see the general thinking behind the design. What we're aiming for here is the ability of the Z80 to load the data. Single input that's fed from one of our already existing in-out port outputs, which we've shown you those previously, and all we need to do is write to a particular port with the data loaded on the data bus, and we can send out whatever data we want, and we then have the ability to generate an interrupt at the end of the process. We have data and inverted data, so we can select whatever driver we want, and this is where I'm going to deviate from my master plan to use only vintage devices. And again, I'm trying to make it clear here that it's not necessarily vintage devices I'm trying to use. I'm trying to show how to go about designing a discrete logic version of a computer system. But what you'd normally do with the receiver and the transmitter module of the RS-232 back when the Z80 was in its infancy is to use a line receiver and line driver IC. Now, I showed the line receiver IC in the receiver module, but I probably won't be using that, and in a similar way with the this transmitter module, we need some way to turn these TTL signals into RS-232 compatible signals. And if we look back at the diagram I made for the data packet, you'll notice that the amplitude of these signals is anything between plus or minus 3 volts and normally plus or minus 15 volts, and that's so it can travel down the long cables that are sometimes used with RS-232. But we need some way of turning our 5 volt signals that we see on the scope here into this. And there are a few options. The receiver's fine, we can very easily just slot in the receiver, it only needs the 5 volt supply. But to generate the plus or minus, let's say 12 volt signals that we want for our RS-232 output, we'd either have to resort to a plus or minus 12 volt supply, so that would be 3 separate supply rails for our system. And I'm trying to keep this as relatively manageable as possible by having just a single 5 volt supply for it. We could of course generate a negative supply just using a fairly simple oscillator and some charge pump circuit, or we can just slot in a ready-made solution, which is actually what I'm going to do. It goes a bit against my design philosophy for the rest of the machine, but there's nothing really to be gained in terms of explanation by using a line receiver and line driver. They are just simply buffer chips that switch voltage levels, and that's essentially what this does. So we can use this one device for both the receiver module and for the transmitter module. This is a MAX 232. It's quite an interesting device. It's a lot newer than we would use for the rest of the machine, but it will save us some aggravation, and it won't really detract from the vintage feel of our design. But this contains charge pump circuitry, so we can run it from a single 5 volt supply. It contains the incoming and outgoing buffers we need for the RS-232 data, but it also, the outgoing data will be switched so that it's being driven, in our case it will be plus or minus 12 volts, which is what we want. And also the incoming data will be tolerant for signals up to plus or minus 32 volts, as opposed to trying to feed those into a circuit using TTL, which would obviously damage the TTL device, and so we'd need to put something on the input, whereas using this we don't. So this will solve quite a few problems for us. Hopefully it won't detract too much from the vintage feel. Comments welcome, but like I said, the line receiver and line drivers, we wouldn't really be explaining the inner workings of those. They're just simple buffers, but using this approach will save us having to resort to multiple supplies for the final design.